Okay, so yesterday we introduced the Hopital's rule, and I want you to find out the example, which is limit x goes to infinity 1 plus 1 over x to the power x. Okay, so has anyone got the final answer after you go home? Does anyone get it, the final answer? I said, okay, you can use the Hopital's rule after that. Has anyone tried? No one has tried? Okay, so Hopital's rule, we know it has to be 0 to 0 form, negative infinity, positive infinity form, positive infinity, negative infinity form. It has to be this kind of forms, okay, the same. 0 over 0, infinity over infinity, negative infinity over infinity. Okay, so we need this kind of form, then we can use the Hopital's rule, and also both the top and the bottom should be differentiable. So what do? We assume this function equals y. Okay, because the power of x here is the main problem for us, so we take ln on both sides. Just give you a little bit kind of like a trick, math trick. Whenever you see a power, the power has a x. Okay, whenever you see the power has x, the first thing you want to do, always try to take ln, because you do not want the power have an x. Okay, if you take ln, the x is not going to be on the power, so it's going to be kind of like a polynomial function, at least not the exponential function. Okay, especially x to the power x. So just a trick here. Whenever you see that, you always try to take ln. So what do? We take ln. Thanks. Y equals limit x goes to infinity ln 1 plus 1 over x to the power x. Once we take the ln, the power can bring it down in front of the limit, in front of the ln. So x goes to infinity, x times ln 1 plus 1 over x. Make sense, everyone? Okay, so now yesterday we discussed this. This is the power 1. Sorry, this is the whole thing. This is 0. This is the infinity form, so 0 times the infinity form. It's none of our 0 of 0, infinity of infinity form. However, we can try to change this into 0 over 1 over infinity form, because keep changing flip. Okay, this is pretty much like equivalent thing. 0 multiplied by infinity equals 0 over 1 over infinity, because 1 over infinity goes to 0. So then, eventually, we got 1 over infinity is 0 over 0, so we got a 0 over 0 form. Okay, that's kind of another trick here. You got this x goes to infinity, this is 0, this is infinity, this is 0. So we put the infinity in as a denominator as 1 over infinity. Okay, so 0, keep changing flip, this is the same thing as 0 times infinity form. And then, however, this will give you a 0 over 0 form. Then you can use the Hopital's rule. So what do? We still have x goes to infinity, and then we have ln 1 plus 1 over x, and then over 1 over x. Now we can see the top, x goes to infinity, the top goes to 0 is ln 1. Bottom is 1 over infinity, also goes to 0, so it's 0 over 0 form. That makes sense, right? So now we can use the Hopital's rule. Alright, so I would like to ask a student help me here. How do I use the Hopital's rule here? How, after I take the derivative, what I got? Can anyone help me with it? Okay, I'll give you 2 minutes. You take the derivative on the top, take the derivative on the bottom. See what you got. Okay, are you done? All right. So, any volunteer? The derivative, top derivative, bottom. Any volunteer would like to help me? Can anyone help me here? I'll just call a student and say if you can help me with it. Taylor, could you please help me with this one?
Could we rewrite the numerator as 1 over 1 plus 1 over x?
Numerator as... Oh, you mean first write that as ln x plus 1 over x?
Would the derivative of natural log be 1
Oh,
over
yeah.
x?
It's 1 over 1 plus 1 over x. That's right. So, and is that all you have?
Then the denominator would be negative x to the power of negative 2.
X, I think it's a negative, right? Did you have a negative? Yeah, negative 1 over x squared. Alright, so now, I have a question here. When you take the ln on this, do we need to use a chain rule?
It looks like we definitely would.
Yeah, we need to use a chain rule. So chain rule of 1, because the derivative ln, we're done with the derivative ln, is 1 over the whole thing. Then derivative of the inside, the derivative of this one, derivative of 1 is 0. Derivative of x, 1 over x, minus 1 over x squared, right? Okay, so the whole thing is just times the derivative, that is 0, 0 plus negative 1 x squared, so it's negative 1 over x squared. Very good. Alright, so what do you see here? X goes to infinity.
It's going to
Lacey?
the x squared is going to cancel with it.
Yeah. Yes. Could you please move that speaker closer to you? Yeah. All right. So these two will be canceled out. I think when you speak anything, you have to press the button constantly. Don't let it go until you finish your presentation. Yeah. You have to push it constantly. Okay. Just push it until you finish it. Then you let it go. So that we can hear the voice continuously. Then we cancel this one. Now my function is 1 over x. So now, can anyone tell me what's the answer of this when x goes to infinity? Lacey?
I think it's going to be 1.
It's going to be 1. Perfect. Thank you very much. Very good. Alright, so now I got the whole limitation is 1. So basically, what I got is I got ln y equals 1. Now, what is y?
One over ln.
Any different answer?
E to
Okay, so it's e to power 1. Okay, this is e. Since we have a natural log y here, we got natural log of e equals 1. So y equals e. Well, if you don't know how to do that, but ln is kind of like a log e, log base e, y equals 1. When you rewrite this exponential form, you just change y equals e to power 1. Okay, so you got y equals e. Previously, we assume what equals y. Assume this limit equals y. So, we got the limitation we just let me see. Can I make it smaller? Okay. So if you look at here, we just assume that limit, the whole limit equals y. So now we got the whole limit equals the limit x goes to infinity, 1 plus 1 over x to power x is equals e. Okay. I hope that makes sense. Alright. So let's look at another. This is the second method of doing the L'Hopital's rule. Sometimes you have to create one form to be able to use the L'Hopital's rule. A lot of problems, most of 80% of the problems will be just very straightforward. You use the L'Hopital's rule, take the derivative on the top, take the derivative on the bottom. There are 20 problems like this kind of problems. You have to make that form yourself, and then you find it out. Okay. So let's look at continue. Look at another problem. See if you can use this one. Use this method again. Okay. Use the value of c that makes the function continuous at x equals 0. Okay. Find the value of c that makes the function continuous at x equals 0. What is the function? The function is defined as fx equals e to power x plus x raised up to 1 over x, x not equal 0, and c, x equals 0. Okay. Why do I define the x not equal 0? Because this one, x is a denominator here. You can look at this function. The x is a denominator right here. So x cannot be 0. So I have to define another number for this function, for this x, for x equals 0 point. Because x equals 0, this function is undefined when x equals 0. There is a denominator on the power here. Okay. So there is a denominator here makes x cannot be 0. Okay. We can't let x equal 0. Alright, so I have defined another value. However, now we want this function to be continuous. So can anyone tell me what's the meaning of continuous function? What's the meaning of continuous?
There wouldn't be any breaks or sharp turns in the graph?
That's perfect. There would not be any breaks or sharp turns or any gap, okay, or any open point on the whole function. For example, if I draw a picture here, okay, even the 0, for example, if I have a point here is 0, okay, this cannot be an open circle. It has to be connected, okay. It has to be connected. If there's an open circle here, it's not continuous, okay. Continuous is different from differentiable, okay. Continuous does, if the function is continuous, it does not mean it's always differentiable. But if the function is differentiable, it is continuous. Okay. Alright, then, if you go if the function is continuous, which means the limit, suppose this is x equals 0. But from left side, x approaches 0. When x approaches 0, the whole value has to be approached to c. So the limit x approaches 0, goes to 0. Although the function is not defined at 0, but it's defined everywhere besides 0. It's defined at 0.000000, a lot of 0, 1, but it's defined at that point. So the function goes to 0. When it approaches 0, the whole value will have to approach the point 0c. Okay. So this will make the function continuous. Does it make sense? Okay. When it approaches 0, it approaches c. When it equals 0, it equals c. Then the function is continuous. That makes sense, right? Okay. It approaches 0, the value will approach c. It equals 0, the value equals c. So basically there's no gap. They're connected. Okay. So it goes towards that point. And then at that point, it equals that point. So this is what we're looking for. We're looking for when x goes to 0, what this limit is. So now I would like you to help me find out what is the limit? X goes to 0, e to power x plus x, 1 over x. What's the limit of this one? I'll give you 2 minutes to finish this. No, 5 minutes, maybe this one. Okay, you can try that. Use the LM method. Okay. Are we done, everyone? Almost. So probably can tell me what you got so far. Can anyone tell me what you got? I think everyone, this is not really a hard one, but since I've already told you, you can take ln. There's a power as 1 over x here. So we just assume this whole thing equals y. Okay, assume this equals y. Alright, you can assume this equals c, that's fine. You can just let this one equals c or y, it doesn't matter, okay. So what do? We have to take ln. So we just let this one directly equal c. That's fine. And then we take, because we have a power on the x, so we take ln. So ln c equals limit x goes to 0 ln e to power x plus x 1 over x. Okay. Then we can bring down the 1 over x multiplied by e to power x plus x. Now what do we have is x that goes to 0 x, oh, I forgot the ln. ln is right here. X is the denominator, so it's ln e to power x plus x over x. Does it make sense, everyone? Because you bring down the 1 of x is the denominator is multiply 1 over x. And 1 times ln is ln, x is in the denominator. Now we can see this is the bottom is 0. Now check the top. X goes to 0, e to 0 goes to 1. So x goes to 0 is 0. So it's ln 1. L1 is 0. So the form is 0 over 0 form. It's perfect. And both the bottom and the top, both the numerator and denominator are differentiable. So we can differentiate, we can take the derivative on top and the bottom. Did you get the same thing, everyone? Yes? Then you take the derivative on the bottom. I'm going to ask a student to help me with this one. So, Thea, could you please help me this one?
So your top derivative is going to be 1 over e to the x plus x, and outside that times e to the x plus 1.
Perfect. And the bottom?
Over 1.
Over 1. Okay. So now we don't have a 0 as a denominator. Even if you plug 0 here is fine. So now can you tell me what's the final answer? Yeah. Plug 0 into here is e to 0 plus 1. Well, I cannot do that. I have to finish one more time, and then you probably can see it better. X goes to 0. Then is e to power x plus 1. E to power x plus x. You can tell that plug 0 into here is 1, plug 0 into here is 1, so it's 2. Plug 0 into here is 1, plug 0 here is 0. 2 over 1 is 2. So I got ln c equals 2. So now, can anyone tell me what's the c here? I'm going to call a student to tell me. Okay, Bella, could you please tell me what is c here?
E to a second.
E to a second, perfect. Thank you very much. So it's e squared. Everyone good? Okay. Alright. One more example on finding c. Find c that makes the function continuous at x equals 0. So function is given fx equals 0, 2x squared, 4x minus 2 sine 2x, x not equal 0, x equals 0. Okay, so I'll still give you 2 minutes now to practice yourself. Okay, are you done? Okay, in order to make this function continuous at not 0, oh yeah, it's C, my bad, C. In order to make this function to be continuous, so we will have when x approaches 0, the function value 4x minus 2 sine 2x over 2x cubed, this one will equal C. Then this is continuous. Okay. So now our job is finding what is the limit when x goes to 0, 4x minus 2 sine 2x over 2x cubed. We check this form first. Plug x into the numerator is 0. Plug x into the denominator is 0, 0 over 0 form. Perfect. And it's differentiable on the top and the bottom. So now we just need to finish the derivative. Okay. I would like to call a student help me here with the derivative. Okay. Luke, can you help me with the derivative here?
Well, you can start out by separating the 4x and the 2 sine 2x.
Yes.
Into separate fractions.
Right.
So like 4x over 2x cubed minus 2 sine 2x over 2x cubed.
Okay, we can do that. We can do 4x over 2x cubed minus 2 sine 2x over 2x cubed. Okay, so then what?
So then as you derive the 4x over 2x cubed, this is going to turn into 0 on top after 2 derivatives. So you can just ignore that, right?
Oh, you take the derivative. This is a 4. This is a what? 6x.
6x squared.
Okay, then you take a derivative. This one, 2 cosine 2x times 2, right?
Yep.
Okay, so what do you got here?
Then you still have the denominator error with 0 on the bottom.
With 0 here. Why do you have 0 here? This one.
Because 0 squared times 6 is 0.
Yeah.
Bottom.
Yeah, we have 4 over 0 in form. This is not the form we want. We only can do infinity to infinity, positive, negative, infinity form, 0 over 0 form. We only have this kind of forms we can use L'Hopital's rule. If it's a 4 over 0 form, we cannot use L'Hopital's rule. So, what do you think?
Can we derive it again?
Here, if you look at this, 4 over infinity, this one, if you plug 0 to here again, so the 4, this one also give you a 4. You see that? Plug 0 into here is 2 times 2 is 4, 4 times cosine 0 is cosine 1, so it's 1, 4 times 1 is 4. So you got 4 minus 4, actually 0 over 0 form. If you do not break them up, you got a 4 minus 4 over 0 form. So it's still okay, we still can do it. But if you break it, we cannot use the problem is if you break this one into 2 fractions, we cannot use L'Hopital's rule. Because this one, yes, we can, because 0 over 0 form. This one we can, because it's 0 over 0 form. But after that, you cannot use L'Hopital's rule again. You have to put them together to be able to use L'Hopital's rule. Does it make sense?
Yeah, that makes sense.
Yeah. This one 0 over 0 form is okay. This is 0 over 0 form is fine. So now after you separate here, you cannot do it anymore because this is a 4 over 0 form. It's not the form we can use for L'Hopital's rule. So it's better we just put them together. We still put them together. We still have 0 over 0 form. You can check it. So it's 6x squared. The top is 4 minus the other one is 4 cosine 2x. Okay. Here we still have 0 over 0 form. We still have this is 4. Plug 0 here is 4. Plug 0 here is 4. 4 minus 4 is 0. Plug 0 is 0, 0, 0 form. So we still can do derivative L'Hopital's rule here. Okay. So we continue to use L'Hopital's rule. Derivative 4 is, look,
It'll be 0.
derivative 4 cosine 2x.
The 8
8.
sine 2x.
Very good. Is that plus or minus? Right here. It's plus because the cosine is negative. Right? Cosine is negative. And with the negative is a plus. So the derivative is, the bottom is, look, what's the derivative bottom?
12x.
12x. Okay. So now do we still have 0 over 0 form?
Yep.
Okay, we still have 0 over 0 form, which means we still can use L'Hopital's rule again because both the top and the bottom are still differentiable. So now could you please continue?
You have 16 cosine 2x.
Okay, over.
Divided by 12.
Now perfect. So now can we plug 0 into the function?
Yes.
Yes, so what do we got?
So then you got cosine of 0 is just 1.
Yeah.
So we got 16 over 12, which simplifies into 4/3.
4/3. Perfect. Thank you very much. You did a very good job. Okay. So we take that use the L'Hopital's rule several times. Okay, several times we got the c equals 4/3, and then we find out that when c equals 4/3, this function is going to be continuous. Okay, so c equals 4/3, and the function is continuous. All right. Does it make sense, everyone? All right. So I want to do one more of the L'Hopital's rule. So can you find the limit x goes to x 0 plus sine x raised up to power x? Can you do that? Okay. Find the limit of sine x raised to the power x. Okay. Okay, are you done? Okay, let's look at together. So still, we have the power on the x. The x has the variable x, the power here. Okay, all right. So obviously, we do not have 0 of 0 form. We do not have infinity, positive, negative, negative infinity form. We do not have all these forms. So we cannot use L'Hopital's rule. We have to do some transformation here. So what we'll do, assume this equals y. Okay. Then L and y, I think that's limit. That's very obvious. You take the Ln on both sides. Then you can bring the x down, sine x. I think everyone knows this already. Does that make sense, everyone? Yes? Okay, this is a very obvious thing now. So we'll try to make a form like this. Now, x is 0. Ln sine x. Sine 0 equals 0. So 0 plus. And Ln 0 plus equals negative infinity form. So when you draw the picture, you want to find out what is Ln 0. So the function is like this. This is the Ln function. Y equals Ln function, right? This is the Ln, the electronic function. So when x goes to 0, the whole function goes to negative infinity. So it's 0 times negative infinity. We cannot use L'Hopital's rule. Okay, this is 0. This is negative infinity. So 0 times negative infinity form, we cannot use L'Hopital's rule directly. So now, can anyone tell me what you need to do here? Take the derivative. if we take the we cannot, because we don't have this. We don't have the 0, infinity, and negative infinity. We need this form to be able to do. We need this forms to be able to take the Hopital's rule. Okay, this one we cannot. So, is there any transformation we can do?
Can they put it over 1 over x?
Very good. Yes, we did this one earlier today as well. And we can put the x as 1 over x. Then the numerator is negative infinity. The denominator is 1 over x. X goes to 0 plus. It's a very small positive number. So the denominator goes to positive infinity. That's okay, because we have infinity over infinity form. Now we can use Hopital's rule. Does it make sense, everyone? Yes? Good. Okay, so now let's continue using Hopital's rule. X goes to 0 plus. I want a student to help me with the derivative at the top. Anyone tell me the derivative at the top?
Would it be 1 over sine x times cosine of x?
Very good. 1 over sine x times. Yeah. What's the denominator?
Would it be negative 1 over x squared?
Thank you very much, Matthew. Very good. And then, what do we continue? Limit x goes to 0 plus still. So what do we have here? So we can change and flip. This is going to be the top is what? Top is tangent x. Top is tangent x. Okay, tangent 0 is 0. Okay, so this is 0. So and over negative 1 over infinity square, so it's negative infinity again. So this is about 0 over 0 form now. So we still can do. You can check that. X equals 0. This is 0. X equals 0. This is 1 over infinity. 1 over 0 is infinity. So 0 infinity. So we cannot use Hopital's rule right now, but we have to change it a little bit. So is tangent x, wait, what, not tangent x, cotangent x, okay. So basically this is is not tangent x, is cotangent x, okay, this is cotangent x. And then this is negative 1 over x squared, so we can change that a little bit. Cotangent x. Like that. Okay. So it's cotangent x times negative x squared. We don't have a Hopital's rule again. You plug 0 into here. This is negative infinity. This is 0. 0 times infinity again. So this is 0. Negative this is 0. Okay, we cannot do the Hopital's rule again. So we can change that into negative x squared over tangent x, because cotangent equals 1 over tangent, right? So now, then we'll plug 0 into here. Is 0. Negative 0 is still 0. And plug 0 into here, 0. So 0 over 0 form. Then we can use Hopital's rule again. So the limit x goes to 0 plus negative 2x. Derivative of tangent is, what's the derivative of tangent? Anyone?
1 over cosine x squared.
Yep. Secant x squared. Very good. Yeah, secant x squared. Okay. So now, do we have to use the Hopital's rule again? So this is 0. Plug 0 into secant is what? What's the secant 0? What's secant 0? 1. Very good. Yeah, so it's 0 over 1. So now the whole thing is just 0. You don't have to do the Hopital's rule again, because this is the numerator is 0. The denominator is 1. So the whole thing is going to be just 0. So I got L and Y. The previous you got a Y, you got L and Y, right? So you got L and Y equals 0. So then you get Y equals, can anyone tell me what is Y? 1. Very good. So I got limit x goes to 0 plus sine x raised to the power x. This just equals 1. Perfect. Okay. Alright. I think that's for the L'Hopital's rule. We are done with the L'Hopital's rule. Tomorrow we're going to do the improper integral. Do you have any question on your homework? Homework 6. I think it's homework 6, right? Does anyone have any question on your homework 6? We have not checked it yet. There is one problem I want to give you a little bit of help. I think this one, homework 6. So okay, this is the homework 6. The first few is okay. You can use partial fraction, use substitution, partial fraction number 4, partial fraction number 5, partial fraction number 6. Okay, 7 we did in the class. Number 8. Number 9 is okay. You have sine theta, you can use use substitution. Then you can use use substitution. It's pretty simple. Okay. So number 10 I think is okay. Number 11 is fine. You can use the formula. Number 12, number 13. Okay. So the problem I want to give you a little bit of help is number 8. Okay, number 8. But we don't have much time. I give you a little bit hint. You can try. You can go back and try it. Okay. So number 8 is from 0 to pi over 2, 5 over 3 minus cosine theta d theta. Okay, this one, because we don't have any formula for this kind of integrals. There is no formula online. What you need to do, you have to do pi over 2, 1 plus 2 minus 2 cosine theta 5 d theta. So you put the 5 in front of that, so it's 0 to pi over 2, 1, and the 1 plus 2, 1 minus cosine theta d theta. Then previously we used power reduced formula to reduce power, but now we don't reduce the power. We actually change that into 1 plus 4 sine theta over 2 square d theta. Okay, and a 1. And then we divide both the top and the bottom by cosine theta of square. So 1 over cosine theta over 2 square and a 1 over cosine theta over 2 square plus 4 sine theta over 2 square over cosine theta over 2 square d theta. What you do here, you got 5 from 0 to pi over 2. You have the top is secant theta over 2 square. The bottom is secant theta over 2 square. And plus 4 tangent theta over 2 square and d theta. From here, then you use u equals tan theta. Sorry, u equals tangent theta over 2. Tangent over theta over 2 square. Oh, just tangent theta over 2. Okay. Then you use u substitution. And d you will use secant theta over 2 square times 1/2 times d theta. So you can tell this one give you du. The bottom you can change it. The u only have u. You can use partial fraction after this. Okay. So then you will have 5, and the top is pi over 2 and 0. This is just the secant theta of 2, so this is du, right? This is du, and over 2. You have over 2 here. You can put it in the front, and then the bottom is u square, because this is u. Secant theta square, you can change in the tangent theta of square of 2 plus 1. So u square plus 1 plus 4u square and du. And then you have changed the boundary as well. I forgot to change the boundary. Okay, so from here, tangent theta, theta equals 0, 0, tangent theta is 1. Okay, so here is 1. So from 0 to 1, tangent half is 0 to 1. So you continue from here, okay? Then this is much simpler. You have 1 plus 5u squared. You can use arctangent again, okay? So this is how you do number 8. Just a little bit help. All right. I'll see you tomorrow, and bring